All right, everybody, welcome back. Let's continue talking about Chapter 3. When we got together last time, we talked about frequency distribution tables. Let's talk now about frequency distribution graphs. The tables did a great job of summarizing distributions of data and being able to see things in a tabular format. But one thing we're going to really like about these graphs is that they allow us to actually see the distribution graphically as a picture. So in this section, we'll learn how to create some of these basic graphs and interpret their results. Let's first talk about bar graphs, dot plots, and Pareto charts. The term graph and chart and plot are often just used interchangeably. So when it comes to the bar graphs, the dot plots, and the Pareto charts, they really specialize in displaying qualitative data. Remember, qualitative data is non-quantitative. So there's no quantity involved, no numbers involved. We'd be talking about data like male and female. Or I think we used previously as an example the brand of cell phone that someone might be looking to purchase. And that data, of course, would be non-quantitative because we'd be getting data back in words like iPhone. All right, well, each bar represents a category. This is an important point, and its height just shows the frequency. It's really relatively basic. So let's look at an example. Here we've got a frequency distribution table representing some grades, and here is a bar graph or bar chart representing the data in this table. So let's just look at it for a second and make sure we understand its basic properties. First of all, we see that the height of each bar represents the frequency of the people who scored in that category. So the people who got A's, there are 4 of them. The people who got B's, there are 7 of them. That's pretty straightforward. Here's a subtle thing. It's really relatively symbolic. Because these are separate categories, we're talking about discrete data. We're talking about non-quantitative data. There's no intermingling of A's and B's. Thus, we have bars that are separated, and you can see that there are spaces between these bars. I know that's symbolic, but it's relatively important in identifying what a bar graph is. Sometimes we can include over here as well relative frequencies. Those are just proportions. So out of all the people, what percentage scored in F, we can see that value right in around there. So let's quickly just kind of go through how we would get some of those calculations. So using the bar graph alone, you see I got rid of the table in here. We should be able to understand the data just looking at the bar graph. What proportion of students earned A's? Now we can see over here that 16% are listed as the proportion who earned A's. And recall that relative frequencies are just proportions because we're talking about how many people earned an A relative to everybody. That's what a proportion is. So if we're going to calculate how many people earned an A based on the data that we see here, we're going to need to know from this chart how many people there were overall. So in essence, what we want to compute is the N. And you might recall that in this situation, the N essentially equals the sum of the frequencies. So let's look at all the frequencies here. 4 people earned an A, and to that we'll add 7 people earned a B, and 9 people earned a C, 3 people earned a D, and it looks like 2 people earned an F. That would give us an overall N, an overall sample size, the number of people we selected, of 11, 20, 23, 24, 25. So we have an N of 25. So we know 25 people earned grades overall. There were 25 people that we measured. We want to know what proportion of students earned A's. So here we'd have the proportion or probability who earned an A is equal to 4 students relative to 25 overall. So 5 relative to 25, 5 over 25. Let's look at our calculator real quickly. 4 divided by 25 equals 0.16. So here we have 0.16, and we can see that that makes sense when we look at the chart and the way it's listed. All right, so they're pretty straightforward, and that's good. Remember, we're dealing with basic descriptive statistics, and the whole goal of descriptive statistics is to simplify our data and to communicate that data in an easy to understand way, and this bar chart does that very well. Let's look at a variation of the bar chart. Dot plots are a variation of the bar graph or bar chart, And all it does is now use dots to show the frequencies. And each dot represents one data point. So here's an example. Here again is our original data based on this grading distribution. You can see this looks just like the bar chart, but now we have one dot representing each of these 4 people who earned an A. 7 dots to represent the people who earned Bs. Now, oftentimes these frequencies, these actual values, are not listed here on the y-axis because remember, each dot represents one person or one case. But you can see if we had many cases, it would be really very difficult to understand how many people scored at each level because we'd have to count the dots. And if we're going to be listing the frequencies right here, we might as well just use bars. It's kind of a strange graph. I don't see it used very often. It's an interesting variation, but clearly if we had a lot of data, if there were a lot of people who scored in each category, we wouldn't want to be counting all those dots. So again, let's just make sure we know how to interpret this. Using the dot plot only, not our table that actually has the numbers, what proportion of students earned Cs? So again, we need to compute our N, and we can find that by summing up all the frequencies. 1, 2, 3, 4 people earned A's. So we're just doing what we did before. 1, 2, 3, 4, 5, 6, 7 people earned B's. So we see we can trust the frequencies. 9 people earned C's. Sorry about that. 3 people earned D's. And 2 people earned F's. All right, so overall, that's the same calculation we had before. That's 11, 20, 25. So 25 people overall, what proportion earned C's? So the proportion or probability regarding people earning C's is equal to the number of people who earned C's, 1, 2, 3, 4, 5, 6, 7, 8, 9, relative to everybody, 25, the number of people overall. So let's look at our calculator real quickly. 9 divided by 25 equals 0.36, or 36% of the people were earning C's. 0.36. So the proportion of people who earned C's is 0.36. The probability of earning a C is 0.36, and 36% of the people earn C's. Those are the different ways that we can kind of interpret that number. All right, let's go ahead and look at Pareto charts. Pareto charts are another type of bar graph that fall into this category. In this particular case, all we're doing is arranging the bars in the order of their frequencies. You'll see it's very simplistic. So here we have some bars representing the number of people, looks like, population in millions in each one of these cities. So about 3 million people in Chicago, 2 million or so in Houston. The only thing we do in a Pareto chart is order these now from the largest frequencies down to the smallest frequencies. So it looks like this. You can see this is really a lot more pleasant to the eye than this is right here, and it helps us see at a glance which is the largest city and which is the 5th largest city. So ordering the bars from low to high just simply makes the graph easier to read and a little bit easier to interpret. Here's an interesting point that I want to make at this point in the lecture. You'll notice that all the graphs we've discussed so far have a y-axis, that's this axis, that has a 0 point. So all of these bars with everything we've been looking at have started at 0. And my question is why? Why is that the case? It's very important. It's good practice to create a graph that starts with our 0 point. Why is that the case? Well, let's go ahead and take a look at this right here. If we display the entire scale, meaning we start at the 0 point, this is for the population, we're starting at 0. If we display the entire scale when we make this bar for each city, then the bars will be in proportion to their frequencies. So their size will be in proportion to their frequencies. And we can see here that it looks like there are about twice as many people in New York than there are in Los Angeles, and the numbers bear that out. 8 million versus about 4 million. So that makes sense. They're in the correct proportion. But now, let's say I wanted to create a graph where I just decided, well, I'm just going to kind of grab them starting at somewhere around here on the scale instead of showing the entire scale. What I'd really be doing is essentially cutting right about here and just taking the tops from those bars and putting them into a new graph. And it would look something like this. And you can see that now the proportion of these bars is out of whack. Now it looks like there are maybe 5 times as many people who live in New York compared to LA. But when you look at the actual numbers, you can see that's not the case. So again, this is somewhere around 4 million, somewhere around 8 million. This bar should be twice as big as this bar. But if we're not starting at 0, they won't be in that proportion. And to make matters worse, when people are creating a graph and they're somewhat trying to mislead you, they might not include these numbers. So imagine that those numbers aren't there. Now this graph is completely misleading, and it does not give us any way to really establish the number of people in each city. So instead of telling a fair and a representative story of the data, some people have ulterior motives, and they want you to think a particular way when you look at their graph. And thus they're essentially reporting misleading information. So we always want to make sure when possible that we have a 0 point there so that we're telling a true story of our data. Pie charts are really good at displaying qualitative data too. A pie chart is similar to a bar chart and the other charts we've talked about in terms of the type of data that it represents, but obviously graphically it's different. So now each slice is showing some categories, relative frequency typically. And when we're talking about relative frequencies, we're talking about the number of Democrats here relative to people overall. So the slice, of course, is going to be in proportion to the total pie. So if 25% of the Democrats represent the whole, we want to make sure that their slice is 25% of the whole pie. You're familiar with these, I'm sure. They're very easy to read, and that's why they're frequently used. And the full pie must sum to 100% for it to make sense. So one bottom line point that we're making here is that we use graphs to tell the story of our data. As a data analyst, we need to break the numbers down and simplify them so that we can tell people what's going on in a very easy to understand way. And most graphs are very helpful in doing that. Here's an example of a really bad pie chart. You can see that this is very simple to read. That's not simple to read. This represents the 100 most active tweeters. There are a lot of people spending a lot of time on Twitter. And we can see that here's the biggest slice, and this represents this particular user. But the bottom line is, look at these incredibly small slices. We have so many different, it's impossible to really make sense of this data. This wouldn't be the best way to tell the story of the data. Here, by the way, might be an example of the best pie chart I've ever seen. One thing that I like about it too, it's showing here pie I have eaten, then pie I have not yet eaten. It's just showing this person is definitely committed to finishing that pie, and I like that. All right, so let's talk about another kind of classification of charts and graphs, and we'll talk about these: histograms, line charts, and stem and leaf plots. And the thing that makes these graphs and charts a little bit different is they really specialize in dealing with quantitative data. Remember, when we're dealing with quantitative data, we have data that has numerical meaning. There's a quantity involved. Let's talk about histograms first. Histograms essentially just look like bar charts, but there are a couple points. The bars are put in numerical order on the x-axis, so from a lowest value all the way to a highest value. And you'll see that the bars touch, showing that the data is continuous in nature. You'll see what I mean with this example. In this particular example, we have a grouped frequency distribution table. So you see that we have these groupings. It's representing the annual energy used per person in millions of BTUs. So it's just a measurement of energy used. And then the number of states that fall within that category, in that grouping. So there are about 16 states that are not using all that much energy altogether. And then we can see some that are using really quite a bit. Total, all the 50 states. Well, we can take that data and we can represent it in a histogram. Because we're dealing with quantitative data and it's measured on a continuous number line, we'll want to make sure that number line is in order from lowest to highest, numerically. It makes sense. So we're starting here with like 100, 200, 300, and of course, 0 is right around here. And now we can put bars to represent each one of these groups. So between 200 and 299 million BTUs, there were 16 states that were consuming that much per person on average. So we would just have a bar representing that. So right here, 200 to 299, we would just create a bar right around here. And of course, we'd want to create a y-axis to show the number of states. So it's going to end up looking something like this. All right. And again, you can see that all these bars are touching each other, and it kind of represents this continuous number line. They're not separate categories. We're simply measuring BTUs, and BTUs can range from none used to lots of BTUs used. So we're measuring the same thing along the whole line, not separate categories. That's why the bars are all touching. And then again, the height of the bar just represents the frequencies. So right over here, there were 19 states between 300 and 399 BTUs used on average. So between 300 and 399, we have this bar, and it goes up to 19. So it's really easy to understand as well. It specializes in quantitative data. Let's look at a slight variation. Line charts are really essentially histograms, but instead of bars, we simply draw a line where those bars would be, and those represent the frequencies. It's also known as a frequency distribution polygon because we're essentially creating a polygon type of shape if you were to view the area under the line as a shape. So these bars are typically gone and replaced just by this line that would show the height of each bar. So it's essentially showing the same data just a little bit differently. Some people would say that the line with the connected dots highlights the continuous nature of the data, and I'd agree with that. It's a good point. Again, it's just a slight variation, really no big deal. So which is the right way to display data? We talked about frequency distribution tables. In this case, it's a grouped frequency distribution tables. We have histograms, and here we had a line chart or a frequency distribution polygon. Which is the right way to display this data? They're all displaying the same data. Well, it's really up to you, and whichever one of these techniques that you think best tells the story of your data. Now in this case, I think maybe this table might be a little bit too busy, but like in a newspaper article or something, it would probably fit in really well. If we were able to use some graphics, maybe one of these two would work out really well for us. It just kind of depends on the situation. In this case, they all do a really good job of telling the story of our data. But I mean, you saw in that one pie chart of Twitter users that told a very poor story of our data. So we do have choices. It's up to us. All right, let's finish by talking about some stem plots. They're essentially histograms that are like flipped on their side, but we're not using bars to represent the frequencies. Instead, we're using the actual data. Let me show you what I mean. So here again, let's look at the BTUs that people are using per capita in the millions. Here I can just show the states that are actually falling in that category. And do you see how it's kind of a nice little play on how we're representing the data? Because not only am I seeing that one state uses all these BTUs, I'm seeing what the state is. And if I want to see how many states fall into any particular category, I can just simply count the states. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 states that use between 400 and 499 BTUs per person. So it's really kind of an interesting way to summarize our data. I don't see a lot of stem and leaf plots in my discipline, but they are used in some. So you'll see them every now and then. So let's make sure we can understand what's going on. Let's look into it a little bit more closely. How many states consume 500 million BTUs or more per capita? So right here I have 500 to 599 BTUs, and all these values represent BTUs above 500 million. So we'd essentially be talking about these states in here. So I'll highlight them. So how many states are we talking about that consume more than 500 million BTUs per person? 1, 2, 3, 4, 5. 5 states. And we actually list what they are: Texas, North Dakota, and so forth. Well, here obviously we're dealing with data that's non-quantitative in terms of the actual states, the state names. Let's look at some different data. This data is quantitative. Here we're dealing with the different countries, and we're going to be looking specifically at this column. This is per person carbon dioxide emissions, metric tons of carbon. So the United States uses quite a bit of carbon in terms of the way that we actually process fuels and things like that. So this is 5.4 metric tons of carbon. Well, we can create a stem and leaf plot based on this data, and I'll show you how it works. It's pretty easy to understand once you understand the little trick. The bottom line is, first we want to establish some type of stem. And then based on that stem plot only, we'll be able to even reproduce the data. We won't lose any information. That's going to be one really nice thing. So we'll have the actual numbers in here as they're presented normally, but when we create this table, this plot, we won't lose any information. So first we want to create some stems, and particularly when we have data here that goes out like 1 decimal place, this whole number represents a good stem to use. And what do I mean by stem? Well, we can see that there are a couple values that begin here with 0 point something, 0.7, 0.3. Then we have like 2.8, 2.6, another 2.6, 5.4, 5.2. So we're going to use that first whole value as our stem. So we have 0 point, 1 point, 2 point, 3 point, 4 point, 5 point. So that's going to serve as the actual stem. Now the way that we produce the leaves is for each individual country that has a value that coincides with this stem, we'll list out the leaf portion of it to kind of finish the number, 0.7. So we're going to have a 7 in here. But I don't want to skip something. There was a 0.3, and 0.3 comes before 0.7. So here I would have a 3. So do you see how we read it? We can see that there are 2 leaves here. That means there are 2 countries that have carbon emissions within that range starting at 0 point. So I see 0.3 and I see 0.7. So I have to make sure that I see that those are 2 separate values represented. Let's see if there are any that begin with 1. I don't see any, so we wouldn't put any leaves. Any that begin with 2. All right, let's take a chance to make sure we get it in the right order this time. So we see a 2.6, another 2.6, and then a 2.8. So we have 2.6, 6, and 8, representing 3 countries. One with a value of 2.6, another with a value of 2.6, and then a third with a value of 2.8. So here we have a 3.0, and that's it. So I'm going to put 3.0. Now do you see how that 0 actually represents 1 leaf? So we can see that there is indeed 1 country using 3.0 metric tons of carbon, but there are none that use 1.0. That's why I left that blank. I don't see any that begin with a stem of 4. And when we look at the stem beginning with 5, we have 5.4 and 5.2. So we're going to put a 2 for the 5.2 and then a 4 for the 5.4. And that, my friends, is a stem and leaf plot. So again, let's say we didn't have all this information there. Could we reproduce the data? Could we compute the mean? And the bottom line is we could. So if we understood what this stem and leaf plot was showing us, we could see that we've got data here and we could start listing it out. 0.3, 0.7, put commas in between here. There's nothing with 1s. 2.6, 2.6, 2.8, and so forth. We have a 3.0, a 5.2, and a 5.4. Could we compute a mean based on that data? Yeah, we could. So the bottom line is we could actually reproduce all the data. Let's just go ahead and finish it up. We would have here 3.0, 5.2, and 5.4. So if we could reproduce all that data, could we compute a mean? Absolutely. Because now we can see real easily we have 1, 2, 3, 4, 5, 6, 7, 8 different data points. And of course we could have seen that from here too. 1, 2, 3, 4, 5, 6, 7, 8 different data points. So we know our n equals 8. All we need to find now is our sum of x. So we know that our mean, x bar, equals the sum of x divided by n. So let's compute the sum of x real easily. Real quickly, we'll get our calculator out. Looking at our data, we have 0.3 plus 0.7 plus 2.6 plus 2.6 plus 2.8 plus 3.0 plus 5.2 and then plus 5.4 equals 22.6. Okay, so back here we've got 22.6 divided by 8. Let's go ahead and compute that real quickly. 22.6 is already in my calculator. I'm sorry, I hit the escape key. 22.6 divided by 8 equals 2.825. So we'll just round that for now to 2 decimal places, 2.83. So this equals 2.83. So that's the average carbon emissions for these countries. And we were able to get that information from the stem and leaf plot because we understand how to interpret it now. All right, well, those are just a couple ways that our data can be shown visually with graphs and plots. That really is the key content from section 3.2, and for now, that is all.